Hello. Today I will give you a course in prompt engineering, prompt optimization, but we'll do it differently. I believe we'll do it better, much, much better. Large language models are wonderful. They work well, but they need to be prompted and they are extremely sensitive to prompts. I have been building AI systems, AI software, code where I call AI for the last 2 years now, and I have scaled some of my products to millions of prompts and millions of document parsing and those type of things. So I've had to build AI software. I've had to build systems with Python where I was calling LLMs and I had to have very good results, but also I was paying quite a lot of money because I was running it at a huge scale. So when you're in that situation, one of the things that you start to really worry about and care about is prompt engineering. You care about the quality of your prompt. Like if I'm running something a million times, I worry that I might not have the best prompt, or I worry that I might have been able to use a smaller, cheaper model if I had a better prompt for that model for the same quality than I have currently with my system. And so, how do you experiment with those things? How can you build a prompt? How can you engineer a prompt in a way that you can be confident that you have kind of, you're squeezing all the juice out of it? Um, and so this tutorial is about that. It's going to be very complete. We will start by covering how automatic prompt optimization works. We will do our own automatic prompt optimization by hand, see how much we improve on a given system with that. We will then switch to DSPy, and DSPy helps us has better tooling for automatic prompt optimization. So we'll do that, but we won't stay with automatic prompt optimization. I will present and we will study DSPy as a tool for prompt engineering. And I'll explain why and how DSPy is a very, very strong and wonderful tool for that, even if you don't want to do the automatic prompt optimization, but rather manual prompt optimization. DSPy will help you organize while you do those things, and it will help you scale. It will help pretty much everywhere. I cannot recommend enough the use of DSPy if you're planning to call LLMs from Python code, and there are DSPy equivalent now in many other code, like there's Axe in TypeScript, there are equivalents in Rust, so on and so forth. This is a complete course about how we can do prompt, how we can quickly experiment and nicely experiment and easily experiment and evaluate our prompts, our AI system in Python. And and so the first step of that, the introduction of that, is just to say, like, now prompt engineering is everywhere. Like, you are on this documentation from OpenAI, and they tell you about prompt engineering. They tell you about tips and tricks. Anthropic has the same thing. And like even Databricks, there was a presentation on their platform by Drew Bruning, and he picked up a prompt from the prompting guide from OpenAI, and he broke it down in many pieces. And so he figured out that only 1% of the prompt was about the task. And so a prompt can contain a lot of things. One of the problems, or one thing that can be hard, is that when all of that structured is all baked and kind of mixed up into a single string, it can be really hard to say, like, here, let me improve the tool definition here. Let me change the formatting instruction. And so you want to use tools that turn that into something more structured. And I'll be presenting those tools here. Prompt engineering, just the last part here. A lot of people say that DSPy is kind of this different tool for prompt engineering. Some say that prompt engineering is dead because of DSPy that automatically optimize it. You can view it like that if you want. Some, it takes care of prompt engineering and optimization details, leading to more reliable, predictable things. DSPy is not your average prompt engineering, using DSPy to enhance prompt engineering with OpenAI, revolutionizing prompt engineering with DSPy, prompting with DSPy, a new approach, automating prompt engineering with DSPy. Like DSPy is really, really, really relevant tool for prompt engineering and for optimizing prompts. Step 1, we will build our own so that we understand better what DSPy is doing and it doesn't feel as kind of black boxy and magical as it may otherwise. And we'll also compare, like we'll get to compare how far can I go if I just kind of naively do my own automatic prompt optimization, and how far do I get to go when I use DSPy, and how much can I experiment with DSPy and push it to the edge. And then what do I get at the end? Like, where is the prompt? How is it? How does it look? How do I use it? All those things. So step 1, we'll here start by using LightLLM. So LightLLM is a library in Python where you can give different model strings and you'll get to keep the same kind of messages structure, the OpenAI standard message structure. And so this is great to easily change models. And it's actually the interface that's used behind the scene in DSPy too. We'll start there. It's not my preferred interface. I actually really dislike this structure of prompting. There's no reason why I would need to say all that and all that. I should be able to only say hello, but whatever. And I clearly don't want all that in my response. Like there's so much of that I don't need to be printed out right away in my response, but it is what it is. So we'll start with this just because it's kind of a low-level general one. And if you do not use tools like DSPy, which you should, you would probably be using tools like that, or even worse, you'll use the library directly from Anthropic or OpenAI, but then if you want to change model, you're kind of screwed. Here I'm going to use Llama Scout on Grok. It's an open source model, so it's nice because I could be self-hosting it if I wanted to. And so that can help a lot with cost, and I could even like conceive that I could be fine-tuning it. So I like to study performances with those type of models where I have more flexibility. We'll be using Grok when we can because it's very, very fast and cheap as a provider, but they have a limited context window. So sometimes we'll switch to OpenRouter, and we need to give an API key. In this case, this is set in my environment, and so I'm just picking it up. You could be putting your API key string here or ask any LLM how to set this up like that, and it would work. LightLLM expects your API key for the providers here to be always named like capital letter OpenRouter, like no space, underscore API key, or Gemini underscore API underscore key, or OpenAI, and so on and so forth. So you have to set these to work like this. Then, okay, so let's just let's just test that it runs. And so let's run that here. Yes, it runs. So the AI says hello back to me. Great. The task today is to extract the before taxes and after taxes amount from images of receipts. It's very simple. I have 11 receipts and I have recorded their before tax and after tax, and the LLM will have to get that right. Some of them are clearly just a number extraction we have to do from the image, but some of them are a little more complex than that, where one of the amount, like the before tax often, is not there. It has to be deduced and calculated based on seeing the taxes amount on the receipt. First thing I have to do is to build my messages that I will be sending to the large language model. And to build that message, I have to create a list, and I will have usually a user message where I'm saying I'm a user and my content will be that. And sometimes I could even have another object there where the role would be the assistant, where I would be saying that was your response. And then I would create another user where I say a follow-up question or something like that. In this case, it's not multi-turn, so we don't have several turns. We just have one. I'm the user and I'm asking something. And so the user will have a content. And so that's another list. And in this case, I have two parts. The first part is my prompt and it's text. And the second part is image. And this is where I give the image of the receipt. That is a lot of boilerplate that it's not great. And that's why we will want to replace that. But it is what it is for now. And if you want to kind of really grasp what this contains, now it's all that, right? You see, that's exactly what we were building, but all together now in one array. And so we're starting this image type, image URL, data, and that's the data. And this is exactly what we can send to the LLM. Then that is the receipt that we are sending. That is the type of receipt. And so you see it will be 45.10. It has taxes related to gas. And so the before tax is not written on this recipe. It would be 45.10 minus those two numbers. And when we bring it all together, this is what we get. So our message is here. And we'll use temperature 0 just so that you could also get the same results as I do. Temperature 0 means that the output will, if the input is exactly the same, the output will be exactly the same. And here we have the result. So the total amount is $45.10. This is correct. And the amount before tax is not explicitly stated, but we can calculate it by subtracting the tax. This is correct. I'm not sure these numbers are correct. I'll need to double check. Yes, these numbers are correct. And now we can also double check the math, because LLMs are not so good at math. And we'll see if both responses were okay. And so 39.23. And yes, that is correct. And so in this case, this simple call has worked. Okay. And that's great. That's a good start. And so we may be here thinking, oh, that's it. It's solved. Llama Scout can do it. But I can tell you that if we run the 10 invoices into it, which you'll see soon, we get only 2 out of 11 correct. So first thing we want to fix, or we would want to do if we're making our own kind of AI program to get those numbers, is that we need a way to extract those numbers out of the response, because that's now just a big string, and we have to have that in structured output, because programs and programming works with structured output. So to do that, we will change our prompt a little bit, and we'll say that it has to put the numbers between XML tags. And let's run that. And let's just get the content out. And we see here at the end that we have the total before tax, and we have the after tax here. So that will be a little bit easier to parse. Let's do a parser. A robust way to parse is to combine regex here. And so you see here, we're extracting the things within those XML tags that we ask the LLM to put in. But a very robust way to do that is to also give those strings that we extract here to a Pydantic model, a Pydantic class. And so here we're creating a class where we say the class is receipts totals, and it has the attributes of before and after receipts. It can optionally have a float. It can be none, because sometimes there will be one of the other that's not there at all. Then we can have a validator that checks that they are only numbers. And also it cleans it up. So It cleans it up. If there are strings, we only pick up the numbers. And here it is. So now we have our before tags and our after tags. And now it's kind of properly structured to go use it in a program. And we can have the confidence that we will have a number and that we can do mathematics on it. And we can do calculations, verification, just use it as a normal variable in Python. So that's a good way to build programs that includes an AI part in it, okay? But now we're starting to be doing a lot of work, and we still have a little bit to do. That is because we're trying to do it all by hand, so we really understand it. Later, all of that will be done much easier for us. And so now we want to measure the quality. And so here we can make a metric where we have a ground truth and a prediction. We look if the before tags of ground truth is equal to the before tags of the prediction. We do that for the other one, and we require to have both. And if we do have both as true, we return a 1, otherwise we return a 0. Let's try our metric. And so here we can give the ground truth, saying that this is the ground truth. The prediction is what we have already processed just above. And we want to see, do we get a 0 or a 1? So now we'll want to evaluate our results. And so that means that we will want to run that prompt 10 times on different receipts. To do that, we will use Pixel Table, and this video is sponsored by Pixel Table. So Pixel Table here is pretty nice because it's like a database or a data frame. It's similar, like let's say to Pandas or to SQLite, but it handles multimedia stuff very well. And so in this case, we can have our receipts image in the database, and we will see just after, we can do computed columns where each time we add a new row to the database, if we have one of the column that was attached to a function and that function was call an LLM, it will be triggered and automatically run. And so you can do very nice pipelines like that in Pixel Table. So here, if it's there and I don't care about it, I'm dropping it. I'm creating a new database. I call it tuto. And then I'm creating a table, receipts. And I am saying what will be the column types and what will I have in that table. And so far, I will have a receipt path. So where the images are. I will have an image. And my primary key will be a path, okay? And then if I look at my file system where I have many receipts and I'm just looping through that, I can insert them all into the table. And at the end, we can look at that table. So let's run this. And then when it's done, here it is. So this is very nice. I really like that we see the images in our table. And so first column of our table is the path. Second column here that we did is our receipt. And so here you see the top 3 receipts. And that gives you a little bit of an idea onto what the LLM is looking at, okay? And now we will put into a function everything that we created before. And so we'll just have a function called extract totals. It will expect a pillow image. And we're doing just the exact same thing. So we are getting our image into base 64. We have the prompt that we were using. We are doing the call to the LLM, temperature 0, image comes here, the prompt comes here. And we're fetching the content, we're extracting it, and we're passing it to the Pydantic class. We're extracting that in the JSON, and that's it. And so now we can have this function that will be a type of receipt extraction tool. And we're giving it one path to one receipt. And we get a structured output that is guaranteed because of Pydantic here to be numbers here, okay? So now we want to run it on all of our images that we have added to that table. To do that, we will use a pixel table user-defined function, so UDF, user-defined function. We just have to specify that the input will be the image and the output will be a JSON, a dictionary, and we're just kind of wrapping up the function we just created. Then we can easily add it as another column. And so this is where pixel table is really nice. You have a new column. I'll call it the extraction column. And I'm saying that this column is defined as doing that transformation on that column. So notice the T dot is the name of my table, like the variable holding that table in my Python right now. And that's it. And so when I'm doing that here, it will do it on all 10 columns. And so that means that it will run my LLM's extraction on all 10 receipts, on all 10 rows, and save the result into that column. This is pretty nice. And then we'll just look at the result with tshow, and we'll get a new column. So here it is. We know that there were 10 rows updated and 10 values were computed. And then we'll be looking at those values. And here it is. So now you have the extraction. And in this case, it's no longer a good extraction, and which I'm now just noticing and kind of wondering why. Because we have the same prompt. Do we have the same prompt as before? Where our extraction was good here. Prompt was that. Let us check. Like it's so, and here, if that changes the results just there, it just proves how sensitive the system is to prompts and how fiddly it is. So extract the after tax total and the before tax total from the receipt. I mean, here, except the minus sign, put these number in, return the value inside these XML. Okay, so the prompt is different here, and that explains it. So strange. We'll keep it like that, just because I ran the whole thing with it, and that's what I know, and I know what to expect and stuff, and that will also match the tutorial in the blog post that I published. But that's a very cool, interesting insight on how sensitive systems are to small prompts like this, small prompt changes. Okay, so we've extracted that. Our goal here is to evaluate, and so for that, we will add another column, column ground truth. It's going to be a JSON, and we use the primary key we said before for updating our table. So we say that, you know, wherever your column receipt path has this value, add this column. Well, this column was just added, but to this column, now add this. And so that will be our ground truth for all of them. And you see here we have a none and we have different things. And so we're just running that. This will be added to our table and it keeps all the results together. And I have a background in data analytics. And so I'm kind of data frame table bias. I rather stuff in that structure often. Just the same as before. Now for pixel table to have a column where it stores our comparison, we are doing a user-defined function on our metric, just like that. And so here we're adding another computed column to our table T, and the column name will be is same, and we're using the metric function we just created, and we'll output that. We'll output the comparison between the ground truth and the extraction, and the ground truth again and the extraction again, and the number, and we'll look at that. Okay, so here it is. You can see that we have only this one that was correctly extracted. So here we have 1 out of 10 that was correctly extracted by Llama. We know that it would have been possible to get this one with a small tweak to the prompt. But anyway, that's what we have now here. And we will now move on to do an automatic prompt optimizer. But just first, I'll show you one last thing with Pixel Table, and it's how now we will leverage everything we have prepared, where we add a new image, a new path. We get that image, we add the ground truth, and it will also trigger the LLM call because our table has some computed. So that is the last receipt we just added. It was extracted automatically for us because we created the pipeline, and it says that this one is good too. So we now have 2 out of 11 that are good. We now have to build a prompt optimizer. And the only reason we build it is not because I believe we'll build something better than DSPy or other tool out there. It's just that it will be very good for us to really understand fundamentally what is automatic prompt optimization doing. In DSPy, there is an optimizer that's already not the latest and greatest because things move so fast, but it's a good optimizer, and it's one that they all work very differently, but they produce the same thing. And so we will study this one here, and we'll try to mimic and make a very simple version of it ourselves. It's called, I'm saying it in French, but it's called MiPro V2. And so the core idea of MiPro is that you have a grounded proposer, meaning that there is a prompt that is given to an LLM in that system that asks this LLM propose a new instruction. And it asks this LLM to propose a new instruction, but it also gives it quite a bit of context. And those are the pieces of context or kind of instruction strategies that can be given to the LLM that gives the proposer, the proposition. And those are things that you will see if you go study MiPro's source code, which I did. And so first of all, it's program awareness. And so another LLM is asked to, it's given the program, like the actual code that you write for your AI program, that would be similar to the code we have above. Like it would be like if we just give the whole extract totals function would be like if we were giving that to the LLM and saying like, hey, can you describe what this program is about? What is it doing? This will be used by another AI, blah, blah, blah. Then there is a dataset summary. Again, it's like if we were giving our pixel table from above to an LLM and say, describe that, what are the columns, what are the information in the ground truth, what is expected, what's the input, those type of things. An LLM would describe that. Then we can actually give a few examples to the proposer. And so we give a summary of the data set, a summary of the program. We give some examples. We can also give it the history of the instructions we have tried in the past and a small tip. So they have a set of tips. Sometimes it's be creative, keep it concise, so on and so forth, so that it kind of tries in different direction. And then what this proposer LLM does is that it looks at all this information and it tries to make up an instruction. There is a second part to that system where it also studies how that AI-generated instruction combines and performs with few-shot example. Few-shot example is when you give to the LLM examples on how it works. So it would be like if we were saying our prompt above, but in the system prompt, we're also saying, and here is an example of what we expect to do. Imagine this was the receipt you received. That would be the output you have to output. And then we can do it several times and see and measure the performance of those strategies. And so in our simplified example, what we will do is that we will have an LLM that does an instruction for us. It will be program aware because we will describe our goal to it. And it will have grounded examples because we will give it, we will ask it to identify and we'll give it some of the errors that we have seen. And then it will produce another prompt and we'll evaluate it. So the first step is we need now a prompt to create the prompt. And so here, you are an expert prompt optimizer, use this information below to learn about a task, blah, blah, blah. Here it would be the current prompt, would be giving it the failures that we have, and we're describing what it should do, and we're saying to give the output like this as in an XML tag, the proposed prompt. Okay, simple enough. We then need to identify those failure cases. And so we'll do a user-defined aggregation in pixel table. And basically what it does is that it looks through all rows. And here the goal is to put into one string all of the failed examples. And so we will simply have to filter our table for where is same is not one. And then we will go through all rows using that to basically just join this string together for all rows. So, okay, and now we have our whole proposer. We're going kind of fast through it because, you know, I'm not trying to teach you how to do that by hand. I'm trying to teach you like what are the steps and how it looks like if you were to do it by hand. And so here is our whole program to do the suggestion, but basically it's everything we just said. We collect the failure cases. We get the images for our failure cases. We give our failure string. We give our previous prompt. We get that all into one big string. And we're passing our images of the failures. And that's it. And basically it will receive the prompt to be creating a new prompt. And we are using a very big model here, so it's a smarter one, and it has good vision capabilities, so it will be able to look at multiple receipts, inputs, output, and hopefully create a better prompt that is informed about what it sees. My hope here is that Gemini will be able to see that, oh, you need to compute it actually sometimes, you need this, you need that, and like kind of detect some of the details and problems that are in that data set and write better prompts and instruction based on that. And so that's our function. That is the initial prompt we had. And we can now run our proposed new prompt, initial prompt. We give our tables and the failure cases. And at the end, we'll have the optimize prompt. And so we're just running it. And so at this point, we have finished making a very, very simple optimizer. Then we could be, running that in a loop, kind of keeping track of the score, looking at which one are performing better, and like trying to see like, if I'm doing 10 cycles, do I get a much better prompt and much better results? And you could be looking at that now and say like, oh, but Max, that was such a bad strategy. You could have done it like this or like that and like that. That's probably true. But then that's where we'll move to DSPy, where they already have better strategies, one, but they also have very good, they have the scaffolding and the tooling to help you make another optimizer. If you have a better idea or you need a special optimizer, you can do it with DSPy. And it will support you instead of you here being on your own and doing every step, kind of re-implementing everything from scratch. Okay, and so that's Gemini response, kind of thinking about it. And at the end here, we have the proposed prompt, and we'll be printing it out, but let's kind of look at the raw string. So proposed prompt. So this is the new prompt suggested by Gemini. Okay, let's extract the prompt and look only at the prompt. So this is it. This is what Gemini came out with. We can see it's much longer, much more detailed. It gives a personality to our agent, tells it to be meticulous. It defines, so after tax, this is final. It can be sometime total, grand total, balance, due. It talks about different characteristic it's seen. It has seen that it's all about Quebec stuff, and so it's mentioning the French version of those names, so TPS and TVQ, and a lot of details and rules. It says that if you cannot find it, you must calculate it. All things we didn't specify in our very, very, very short prompt. That was just that. We're saying like, hey, just extract those and put them into the XML. And so this probably works. Like, it's probably better, right? And that's what DSPy does, but better. Okay. And so now we're modifying our function a little bit that we had before for pixel table to do computed columns. We had only extract totals, but now we want to give it a prompt because we will be changing that prompt because we have a prompt optimizer. And so it's just, extract totals with prompt. Same thing here, just the prompt is being passed through, okay? That's it. We're making another user-defined function, and where here we have our proposed prompt version 1 we just created, and we're thus having a UDF extraction version 1. We will be saving that into column version 1, and so just another column into our table, and we can look at it. We will make sure that we compute that on all the rows by adding a computed column for the metric too, and then we'll look at all of that, just getting the mean of this. And so because we are in a table here, it's kind of SQL-like, pandas-like, and so we get those functions where we can just simply do a mean on that and get our results. And you'll see from this output here that it's kind of all organized in one table, and it's kind of nice to track our progress here. Oh yeah, coffee.
Correct.
Oh yeah, coffee. And we have just finished running the extraction. So the LLM's calls stored in a new column on every rows. We now have 11 rows, remember, because we inserted one after the fact. If I was to insert another one right now, I will just trigger all of the computed columns, all of the metrics will be computed, everything will be added to that. So I could come here at the end, I'm done developing everything, and just add 1,000 more images, and they'll just all be triggered in that pipeline. So this is a feature I really like about it. This is not more true, and it's still the same. This is now different between these two, and it is now in fact correct. And so we seem to be improving. Yeah. So now we are at 36%. 4 out of 11 that are good instead of 2. And so we have optimized and we have improved. Okay, so let's drag that here, just like that. Boom. Okay, 4 out of 11. We just did automatic prompt optimization by hand. It's as simple as that, and it works. So and we could put that into a loop and kind of automate it. But let's say that we just do a second loop for now. So we put now our prompt version 1. We are getting our mistakes from version 1 now, and we will be saving our results in version 2. So Gemini is going to think hard about it, try to write something better for us, and we will extract it and look at it when it's done. Okay, so this is an even bigger prompt. It gives stricter step-by-step kind of rules and ways to approach that. Let's evaluate it. And so now we're starting to kind of have our infrastructure set up for Pixel Table, and we're moving through, and like we can now move faster with less code. And so here we're leveraging our extract with prompt, where we're giving our second prompt, making that a UDF, applying that to the receipt image, storing the response, giving the response here into our metric, storing that into another column, looking at the values in that column. And yeah, so now we will trigger the extraction for all of them. Okay, that's it. Now we have 1, 2, 3, 4, 5. So 5 out of 11 are good. So we have further improved. In my previous test, I had gotten 3 out of 11. Now I'm wondering did I not set my temperature to 0? Interesting. Okay, so now we're doing the optimization with Maverick instead of Gemini. And here we're doing it with Gemini. Interesting. Okay, cool. So last time I used Gemini twice to improve when I was creating the tutorial. And I gotten on the second step actually worse results. Here we changed to another model and we have further improved. And this is a thing I've seen often where model changes, they kind of compose together and improve together. Like model merger is something I really like to do. And so here it is, just small tips and tricks for you. That's pretty cool. Okay, so now we have 1, 2, 3, 4, 5, like we said. Okay, 5 out of 11. Let's look at all of our scores so far, one next to the other. And there it is. So at first we had only 2 that were correct with our basic naive prompt. Then we got 4. And by giving our prompt again to the optimizer again, this time with Maverick instead of Gemini, we have gotten the first one right too, which we knew we could get, right? You remember just before we evaluated, in our first test, that was correct too. We had gotten that right. So 1, 2, 3, 4, 5. Now that wraps it up for doing it manually. And so you can see the only thing we're doing is give it some information about what we're doing, passing some kind of feedback onto our failures to an LLM, ask it to write different instructions, and run those instructions on many cases, evaluate it, okay? This is pretty much how the crux of any automatic prompt optimization. Now we'll move to doing automatic prompt optimization with DSPy. And then after that, we will move to optimize our prompt further, but with non-automatic techniques that are more about how do you program or structure the prompt. Okay, so if you're not used to DSPy, this will be the kind of simplest way that you can call an LLM in DSPy. That string is the same as we used above with Light LLM because DSPy here wraps that library. And so this is much simpler, it's much better. Just a simple hello, that's what I wanted, and just a simple answer. None of that, big message, dictionary, array nonsense. Beautiful. One thing here that might trip you up is that I have set my API key here, and this works just like Light LLM, and so it will be the same thing. If you want to give your API key, you would do that here. Equal, and then your key here, okay? And if you're wondering, again, what would be the name of that environment variable for the key, it's all in Light LLM documentation. Okay, so to make that programmer, that that prompting in DSPy, we will here use almost the same technique, but we will skip the parsing because DSPy will do it for us. And so this is the same as we had above, right? You remember that we had a Pydantic base class, we had a before total, after total, and they were optional like that, okay? The difference now is that in DSPy, we're doing a signature instead of a prompt. One of the fundamental idea of DSPy and one of the reason why DSPy is so nice to experiment with, so fast and so flexible and just like all around awesome, it's because of this here. It's because of those signatures here, okay? So the way to define a signature is to do what is in Python. If you're not used to classes, that would be called subclassing. And so it's the same, like here we were doing a subclass of base model. Here we do a subclass of signature, okay? in the signature, in that object, whatever you put here will be saved as the instruction. So this will be equivalent to the part that we were optimizing above, okay? And these here will be automatically turned with a template that they are called adapters in DSPy. They will be automatically turned into instructions to the LLM for us. And so we don't have to worry about saying like, here is what I'm going to give you. Here's the image. Here's the, I expect you to give me a receipt total formatted in whatever way. We don't have to do any of that. DSPy does it, and DSPy does the parsing for this output. And if we say that the output has to be receipt totals, that information will be that information that we expect a receipt totals will be put into the prompt for the LLM for us, and the corresponding proper extraction will be done for us. And DSPy will also even retry. So if it fails to get this receipt and we have not temperature 0, it will retry, and that may give a chance to the LLM to give a different response, and maybe it's going to work this time. There is also more than one template in DSPy, more than one adapter, and the default one will try in one way, and if it doesn't work, it will try with a different prompt, different template, where it asks to return it into a JSON template instead, and so then maybe it's going to work there. We'll look at all of that just right now, okay? But that's it. That is how I define my whole thing. Everything we've been doing above, except the optimization now, all fits in this screen right here, okay? So program here. Let's, just for so that it's very clear for you, let's just print this, okay? And so this is what it holds. You see that it says that you have a program where your input will be a receipt image and your output will be a receipt total. That's what I wrote here, right? Input field, receipt image, output field, receipt totals. There will be instructions, and the instructions would be those. This is what I have here, correct? Now, there are two fields, and this is of type image, and this is of type receipt totals. They're both required, and they will be presented to the AI like this. So receipt image, see the underscore was removed, capital letters were added, underscore was removed, capital letters were added. And this is the signature object, and this is what the DSPy code behind the scene will use, study, manipulate, move around, and then if it wants to optimize the prompt, it will change that here, the instructions here. There is somewhere else, and so let's create a program from that signature. So we have a signature, it looks like that behind the scene. We can create a program with it by wrapping it up with DSPy predict, and so now this signature is a program. We can give it an LLM to use, and that is this one. And so at the end of that, now we have a program, and so it's a structured, it's a Python object that says, okay, I'm a program called predict. I will be using that instruction, but it has more. This program knows which LM it's supposed to call. And so get LM, let's say, it gets a reference to the LM here. And so if I'm calling it like that, I'm using that one that I have defined. And so it's easy then to have programs that each have their different language models attached to them. That's one useful thing that the program does. Another thing is that it contains demos. And right now this is empty. But if I wanted to do few shot prompting, I could be adding demos here by hand. Usually people don't do it, but this is what Optimizer will do. Optimizers will add demos here and try to run the program with that demo and see if it helps. Optimizers will change the instructions here and it will run this program and see if it helps. I have to give it an image, right? So receipt image equal, I'll have to use the DSPy image here because this adds some decorators that tells DSPy how to handle that base64 string. And so it would be like that. Okay, so DSPy from file, I'm giving it a file. Now this is my whole program. This is how I'm calling it, and boom, I get my results. And it says there are none before tags and there are some after tags. Notice here, it's not magically better, like it didn't one-shot that perfectly well. And that's fine. Nobody claims that DSPy-based programs are better than your naive prompts, but they are easier to experiment with, and they have the tooling to then get better. And so now we will reuse and leverage the infrastructure we have with Pixel Table to do the evaluation. But DSPy also has its own evaluation toolkit, which we'll use later. I'll show that to you. But if we want to compare DSPy to what we have been doing now, it's just the same, right? We are doing a user-defined function for our DSPy baseline program. That's the program. And for each calls and rows, we'll give it an image pillow. And so DSPy can do from file, but it can also do from pillow. And we'll dump the results. So we'll capture the results. So dot receipt totals, that's the results here. And we'll dump that as a JSON as we did before. Okay, so let's run that. So 2 out of 11 are correct. This is exactly the same result as we had with our naive light LLM prompt. So not worse, not better. And we can also run them all one next to the other and see if they fail and succeed at the same place. You see it succeed at the same place. So those two receipts are probably a bit easier. And that's where, when you have a base naive prompt, that's where it works. But because we're not telling it at this point to do the calculations and all those things, it probably doesn't do it, and so it fails. Okay, now we'll do the automatic optimization with DSPy. To do automatic optimization in DSPy, we need a training set, and it needs to be in the shape that DSPy expected. Before we were doing in our own shape, we were using Pixel Table for that, but now we'll need to do a list of examples, okay? So this is very similar to what we had before, so we have our path to the image and we have our ground truth. That is right now our gold set. What we will be doing is that we loop through that gold set, and for every element in that gold set, we create a list of examples. Our examples, to create them, is that we just have different arguments, and those, we give them the name we want. And so here I have one called receipt image. I have one called receipt totals. I'm using DSPy from file with my particular iteration in my gold set, and I'm getting that path here to be assigned in that receipt image as file. So now at this point, it's going to be a DSPy image object stored in that element in that example object. Then we have the receipt totals. And so we want the before and after. And so we're getting the ground truth before, we're getting the ground truth after. And for DSPy to know what is an input and what is other things, because you could have many things in your examples, it doesn't kind of mess up with DSPy. They're useful to you for a different reason about metrics, and some recent optimizers also might make it so that you want kind of more elements in your examples than your inputs and ground truth. So you have to tell it what is the input. And so the input here is this receipt image. Okay. And so at the end of that, we get a list. Okay, so let's also look at it. Look at that. Boom. We have this image. It's dictionary. First thing is this. It has the base 64 encoding things and the results, and we know that the input key is that. Okay, nothing weird, nothing fancy. Just a list of examples. We will then have to do a metric in DSPy, and the metric in DSPy is very, very similar to the one we were just doing. So this was our metric. This is what we had. And for DSPy, we have to do this. Okay. And so pretty much the same, like instead of giving our ground truth, we give our whole example object. We can give our prediction. We have to give the prediction. And we have this trace none. And this is used in some cases for the few shots details that for now you don't have to worry about. Just know that you do that and it's fine. And so just the same, right? So this is the same, this is the same. This is all the same. So what changes? It's because we're not just passing ground truth now, we're passing the whole example object. So we have to go get our ground truth holding element within it. And our prediction is a little different because we get a prediction object. And so we have to go one step more into it. That's it. Okay. And this is the optimization now. So it's that simple. There's no more code than that. And if we want to kind of clean it up and really kind of see the whole thing now on like how much code do I need to do optimization in DSPy, you would need this here. Okay. You need that. You define your program. You make it into a program with predict. You set its LLM. Then you create your training set. And you create your metric. And you bring all the pieces together here. Let's walk through it now. This is our program we had. We will make a deep copy so that if instructions are changed, they are not changed everywhere, and it's required. And so we will have a teacher program, and our teacher program will use a big LLM, and that teacher program will be given upon the compilation here. Then we are setting up our optimizers with some options. We'll use MiPro, the one we explained above. We are giving the metric that the optimizer will try to optimize the program for. In this case, I say I do not want it to use demos. Those are the few shots, because I want it to be similar to what we did above. Okay, so no few shots here, just instruction optimization. The model that will be writing the prompt, I want that to be Gemini again. And here I can decide between light, medium, heavy, or I can have a suite of parameters that decides kind of how many loop it does and how hard it works at making those things. So I'm going to use medium here. So that's the optimizer. I take that optimizer here, bring it here, and then I start a compilation of that, which compiles that program, not the teacher one, but the original one we had, which has our training set or eval set. It's this here. It usually MiPro asks you if you're okay because it tells you how much it's going to compute, kind of how much it's going to cost. It doesn't give it in money, but in kind of effort number. And I just don't want that to I just don't want it to ask for my confirmation, so I'm just saying false, and I pass my teacher program, and that's it. This will run, it will run an optimization, and that will be my optimized program that I can use afterward. And so we see here all the prompts that Gemini have produced. And so the first prompt is our simple prompt. Then here there was another prompt. So those are all the prompts. And now MiPro is evaluating them. And so, it has just figured out that one of the prompts is 62% on the 8 examples that it has kept for the evaluation. And so it tried different prompt, 25, 25, boom, 62. Great. It continues evaluating. It has stored the fact that our best one so far was this. and it will do those evaluation 18 times. And yeah, and at the end, it will store the best prompt for us. So it's progressing through it, just rerunning all of them. And now see, we have a couple of them that have 62.5%, and it should be done soon. So each time that it goes through that, our Grok Llama 4 is being asked again and again to evaluate. So you have to be mindful. There is a cost to that. Usually it can go around $2 or whatever. Like, it's not ridiculously high, especially if you're using a smaller model to do the task and a bigger model to do the prompting, because the prompting is just like 12 prompt, so that's not that much. But the evaluation would be something like 8 times 18. And so then you're closer to like 100 prompts. I have no idea why we have a 19th trial out of 18, but it is what it is. We even have one here that is at 0. And so best score was 62.5. And let's try it. We're running that. Llama as insert. That is correct, if you remember. Let's look at this now, okay? So this is our current optimized program. And this is the exact prompt that was sent. Okay, so the system prompt, this is one that is on top. We have not set a system prompt in our naive light LLM system. The system prompt here goes along like that. So your input field are receipt image, it's an image type. Your output fields are receipt total, it's a receipt total type, totals type. All interaction will be structured in the following way with the appropriate value filled in. So it tells the LLM that it will be told the user will say this, and the receipt totals structure and output expectation is like that. And it's completed. It will have to say that it has completed the task. And then that's also part of the template here. So in adhering to this structure, your objective is, and this is the instruction. So this whole part here is what Gemini was working on, and it was being templated into that. And those values here are taken from our signatures and they're templated into the template. And it's the template that decides to use those demarcation. We can write our own adapter in our own template. So that's one modular part on which we can manipulate the prompt. And so this is why I'm saying DSPy is a good tool to optimize your prompt, but not only automatic optimization, because one optimization you could be doing in your system is the templating. You could be changing that templating. Maybe it's something you need. I personally need it sometimes. Okay, so that was the instruction that was automatically created. And this is the specific interaction we just had. And so what we said as the user is this. We said that the receipt image was that, and this was given properly to Light LLM, like in this content type, as we were seeing before. And then we said, as if we were the user, because of the template, the adapter template, we said, respond with the corresponding output field. Starting with the field, receipt totals must be formatted as a valid Python receipt totals, and it should know what this is because we said it here, which was automatically put in there from our code for us. It was done for us automatically. And then ending with the marker completed, okay? And so this was the AI response. Okay, so the AI response was now here very clean, very well formatted. And then a parser took it and made sure that it was turned into that prediction objects that holds the answer which was receipt totals because that's how we called it in our program. And so in our programs here, we said that the output field here was called receipt totals. And so that name here is the reason why we have that here. And it's the reason why if we want to grab the results, let's say we are rerunning that. And DSPy does some caching also for us. So let's say results here equal, okay. So results, so you see it was really fast because DSPy does caching for us. And so that's how we can fetch it. And this is of the type we asked. And if we want, because it's this identic thing, it supports that way of fetching data, okay? So DSPy offers all of that to us. Now the question is it better? Did it help? Is it worse? Is it better? Is it equivalent? In all cases, in my book, if it's equivalent, it's better because it's easier to code and more structured and all those things. Like it's just a service that the DSPy API gives to us. Here I have a little bit of code that helps us just get the actual instructions. So in the program, there are named predictors because DSPy programs can actually contain subprograms. They can be like a hierarchy of programs, and the optimizer will go and optimize all of them. And so that's why we can grab our named predictors. In this case, we have only one, and we would have to loop through it and get our predictor and look at the actual signature instruction that we ended up with. And there we can print the actual instructions that we're currently using, the one that were optimized. As before, we will now bring all of that into our pixel table, and we will again do a UDF for our optimized program, and we will run that, and we will look at its performance. So if I remember properly, our best score so far was 5 out of 11. This was our second step optimization, which we ran with Maverick on top of Gemini. And here we'll be comparing them all. So DSPy base, the base naive, optimization 1, optimization 2, and DSPy optimization. And here, DSPy programs can be saved. And so you can actually save the program on your system. And I have done that previously. So while it runs the compute here, let's go look at our DSPy optimized program. And then you can load it back. And so we don't use traces. We didn't save the training data. There was no demos. We didn't do few shot optimization yet. We'll try it just after. But this was the optimized signature that I got last time. And I saved it like that. And those were the fields that we had in our programs. There was receipts image, there was receipts total. The large language models that we were using was Grok that we had assigned to that model. Our type, like interaction type, was a chat, temperature 0, max token 4000, non-retroized tree, all those things, and then dependency version and so on and so forth. So all of that was saved for me, and so I can load it back and get my program back without recreating my signature and resetting my instructions. It's all here. While this runs, we will move on to few shots example optimization. So let's just, few shots, auto opt, okay? To do few shots, I'll need examples that are candidates for few shots. And I wasn't so careful right now to evaluate on the examples that we're giving to the LLMs because the LLMs are writing very high level queries and they generally don't go like, okay, like if your receipt has this subtotal, the answer is that. Like they don't kind of hard bake the response into the prompts like that. So I wasn't too worried about that. It wasn't like perfect setup, but still what I'm doing and I don't really worry about it. But in this case here, we will actually shove in there some examples for our programs. And so because of that, I'm creating a separate set. And so just as before, this is all the same of how we did the examples before. We create an example set, but this time it's going to be train set instead of eval set, okay? So we're running that. And now we will be running pretty much exactly the same optimization as we had before. This time we'll go with OpenRouter because we are going to give it few shot examples that includes images. The context will start to be quite big. And so to have that big of a context, we need to use other providers than Grok. So we're changing that here. See, super easy. Changing provider, changing model, extremely easy, super nice. I'm setting that model at the global level here because I'm not quite sure why, but MiPro to work with the few shots example requires me to have a high level complete global LM. So I'm setting that here. Doing the same copy here, but now I will actually start from my optimized program and see if adding examples further help me. A note is that because of the amount of context this will take and the cost of the call of this program will be higher, I will only keep it and consider it if the quality is actually quite a bit increased, because otherwise the cost wouldn't be worth it. As before, I have Gemini that will be my teacher model. Let's make that big. I'm setting that here. Now we're setting MiPro, and in this case, we're letting it have some demos or few shot examples. We're not setting that number too high because of the images. It's already quite big. This is the model to prompt. Give it more context. Again, same things. Let's use some threads. The task model is this base scout model, so on and so forth. The metric that we did before. Everything else here is the same. The thing. And now we have a training set and we have a validation set, which we just created, and we'll be running that when we have our results here, which is getting quite slow. And I really think I'm being throttled here. So there's probably some like sleep and exponential backup or whatever because Grok probably doesn't want to answer to me. So it finished. So we have 5 out of 11. So we're not actually better here than our custom prompt. Here the custom prompt was getting that wrong. Now this gets it right. But here it was getting it right, and now it gets it wrong. Super interestingly, our custom manual optimization has cost a lot less because we just ran it once. We didn't do like a thorough evaluation. We just did 2 loops, but we baked quite a bit of information into our prompting prompt. In one case, you could say, good, I don't need DSPy. I can just use your prompt max and get it optimized. I'm sure. I mean, I hated coding yet, and so I much rather the story where you say, I will use DSPy because I get the same results as whatever I did by hand. But also, this was just one optimizer. I could be using other ones. That was only with Gemini. I could stack Maverick on it now. I could run other optimizers. The code to make the program was easier. I can save the program. I can load the program. I have so much service in DSPy for the development here that makes it so that I much prefer DSPy. But again, nothing is magical. You can also code it and get the results. Okay, so we're saving that. And now, as we were just discussing, we'll run those few shots. And so now we'll try to add few. Last time I ran, few shots didn't help at all. But one thing, again, that I like about DSPy is that it's quite simple to try it out, experiment. Does few shot help? It doesn't. So now if your manager comes to you, or if you're yourself making your own like application using AI, and you're like, damn, you have this feeling, oh, maybe I could be better if I had used few shots, or the manager's like, hey, go try few shots. Well, just a couple lines of code. We modified like 3 things, right? We modified this here and this here, basically. Had to have our training, but that's the same code as before. And now we can run it, get the results. We know empirically, yeah, no, it doesn't help. It's too costly. We're not keeping it. We're not doing it. Okay. Super fast, easy experimentation. We will here be printing the demos, if any, are set, and the instruction if they are further modified to pair well with the demos. After that, after the few shots stuff, we will be done with the automatic optimization, and we will do manual program crafting type of thing. And so manual program crafting here, it's about modifying our program here, which has also the step of, to create a program is this, right? This here, like that. Pretty much all of the knobs that you can play with. There are the modules, but I don't want to get into that now. I have not used them much, and so I cannot say that I don't recommend them. I just have not found that I needed them. The last part will be demos, actually. So you could set demos manually here, like that. And it would be an example, I believe. And so if I'm, let's say I'm taking my train set, that was a set of demos, I could be doing that. And then that would make one few shot example to my program. Here, you're looking at that. It's code. It's kind of simple, kind of verified, manipulatable. If you are programming an agent, or you are programming a workflow or AI program like we do here, I believe that you're much better doing your prompt optimization or prompt engineering in that interface than it all in one string. But why and how is that prompt engineering? This is because all of the pieces together in the end get composed into a string. And the chat adapter is responsible for that. And we will look at it as soon as this is done running. And let's look into that, okay? So let's kind of decompose. The chat adapter will receive and expect a signature, a language model, and demos, and it would create a string, and maybe not even a string, it will create a message. So at the end of the day, what our adapter does is a call like that. And so the prompt, this one, is created for us by that. We can change it if we want to. We can affect that. So that can be one element, one module, one modular way that we can optimize or engineer our prompt. Is what is the template where things get baked into the prompt. Another part that we can engineer it is by choosing our few shots examples and choosing if we do some of them. So those would be here. Another thing we can change, it's the style of prompting or behaviors. Here we're doing nothing, like we're doing it vanilla, but we could be changing that with React. And now it will be an agent that would be calling tools in a loop. And we'll cover that just after here. I don't have the right syntax here, but it's something like that. And then you put Python function, like my fun, something like that. Okay. That is one other knob of optimizing, because here we will be composing a prompt that tells the LLM, well, actually you have tools and you'll be running in a loop. And so you can answer with a tool call. I'm going to run that. I'm going to give it back to you. You're going to interpret it. And at the end, you're going to give me an answer informed from your tool calling. So could do that. Another thing I can do is, instead of doing the basic predict, I could do chain of thought, where that would make it so that it actually kind of modifies the signatures, and it modifies then the instructions in the chat adapter that will make it so that the LLM is told to output a reasoning before it outputs the outputs. And so this does that. And so if you want to make your LLM reason and see if that improves, you use that. That, again, changes your prompts. We will try it just after. And another thing you can do is that you can say, well, maybe I'm going to try to give it more information or different information. I could add here another input if I wanted to, and it could be receipts, description. And maybe what I do is that I call another AI just before. We won't try it now, but it's a thing I can do. And I can call another AI, and that can be like an AI text description of the invoice. That is another thing I could do that would affect my prompt. It will change the system prompt because now my system will know that it will be given that description, and it will change the way I'm calling it because I'm going to give that description to it. And so now I would have also two calls to two AI. So first one AI describing it, then another AI receiving the image, the description, producing the output. Maybe it would help the performance. It would increase the cost, but maybe it would help the performance. I could also decide to do reasoning myself. Let's say I'm not using chain of thought, but I'm doing reasoning like that. And so I could be doing this input, blah, 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 right? My input field. And so now it would have to do reasoning. I could change the order. If I do this like that, it would be a bit dumb because models are autoregressive. So you want to do the reasoning before the response. But if I change that, it would change my prompt. I'm engineering the position that the AI will be generating the output. I could be doing some intermediary steps, which we will see just after. And so I could be doing something like list numbers. And I have that just below. But basically the idea is that I would make it do a list of floats of all of the numbers that are found into the receipt. So something like all numerics related to money on the receipt. And so the effect of that would be that the LLM would kind of have to focus on extracting all numbers first and then think about finding out of them and maybe doing like maths on them to give me my results. That would be an output. I don't have to put that output in my metric. I don't even have to look at that output. I don't have to care about it. But by doing that, I am making the model do it. Again, I could play with my structure. I could try to have the numbers after. Pretty sure it's not going to help because they are autoregressive. I prefer to have it before. But that is another element in my prompt engineering activity and steps. In my experiments, it's another experiment. I could be changing my instructions. Maybe those are not the instructions I want to give. And again, I could also try to split it up into two. And instead of doing a receipt total, I could be just asking to extract the before tax, and that would be just a float. And I would change my instruction, and I could also say instructions here on what to do for that number extraction. Then I could be doing another signature, doubling that, do two calls, pass 2 times the program, but then this time I'm doing an after. And that would be simple like that. This is very, very easy and fast to experiment. That would be like, let's say intent 1, intent 2, that's intent 1, program. I'm just kind of showing you how fast I can iterate and see. And so now I have those two things, program 1, program 2, would be calling both, putting that into a metric, and so on and so forth. Super easy, super fast to iterate. At each point, each thing I'm doing here, I am changing the string that is given to the LLM. I am engineering that string, but I am manipulating higher levels of abstractions of that string instead of fighting with every single characters in it. Okay, are we done here? Best score 54%. That's what we had before. So it's not better. 5 out of 11. It has evaluated that. It's not better. Let's look at it. If it's not better, I believe it will choose to stick with what you have. So see, it didn't add any demos. This seems quickly like that just to be the same prompt. And so it just says, yeah, optimized it, tried it. It's not better. Your optimized program is actually the same program. That's it. So let's not delve into that more. Now let's actually run what we have been talking about here. Yeah, so I actually want to demo the chat adapter here a little bit better. Okay, don't dwell on that now, but there is a shorthand version of doing the signatures. Instead of doing this class here, you can do it in a string like that. This is what this does. Then I have my inputs, which I will be giving like that's if I'm calling the program, I will be giving that input like question equal that. And in this case, I am providing just my own demos because that is what the chat adapter will see. It will see a signature, will be seeing inputs, and it will see demos. And from that, the adapter will format them into a string. Let's look at it. And this is it. You see this now, the thing we've been talking about from the beginning. You see that we have an array of dictionaries or JSON that has role, system, content. That's the content, role, assistant, content. And here you see assistant, and you see user, and you see another user somewhere. Let me find it. Role user here. So role user content, role assistant. That means that is the few shots. That's how it's rendered with that particular adapter. If I change the adapter and I'm using the JSON adapter instead, the prompt will be different. And the way that the prompt will be different is that here, for example, it would say respond with a JSON object in the following order of fields instead of respond with the corresponding output field, starting with the fields this and then ending with completed, so on and so forth, right? It's the same prompt, but on the format part, it's been rendered differently. Now that you have like a complete kind of view on how we do manual prompt engineering or crafting while programming in Python, we will be doing a little bit of that and see if we improve our program further. So the first thing we will further try is we will try to do reasoning. We'll try to get our model to do some reasoning. So that's our prompt. That's the program we had before. We are now changing for change of thought here instead of predict, setting our LLMs here. Again, going with Grok. We'll do our evaluation now. We'll do it with DSPy. So DSPy has this evaluator you can create where you give it the evaluation set, you give it the metric, you can thread it so that it calls Grok 5 at a time, receive the response, and display it. So let's do that. And now we have 7 out of 11. This is our best score so far. And I have not used our optimal prompt here. I've just used one of the basic prompt I had at the beginning. Let's try that prompt. Let's try the optimal prompt. Do we get better results? Or is the reasoning the most important thing? One useful thing here is that if this doesn't give better results, we prefer to use the other one because it has less token, meaning that if we run that at scale, the cost would be lower. Let's do an evaluation of that and see how I'm iterating through that really fast. So let's get our results. Okay, 8 out of 11. It's a little bit better. Does it matter that much for us? Maybe that's like, maybe we need that performance and the cost of that addition is okay to us. Let's try something even more advanced now. We'll try to turn it into an agent and give it tools, okay? So here I'm defining a Python calculator function. To give tools, it's very easy. I'll show you how we will give tools before I get into the functions. Look at that here, okay? Turning our whole thing into an agent is just like that. And so we still have our signature. Instead of chain of thought or predict, we do react. And we give Python functions here, and that's it. That's just it. It's going to run for us. DSPy will run those functions. If Llama Scout wants to use them, Llama will get the response back. It will iterate on that, give us a final result. And so if I want to see, if I give it tool and I run it as an agent, if I get better results, just easy like that. Now I need to define those things. Maybe they exist already and I'm loading a Python library to use them. In this case, I've just asked some LLMs to generate those for me. One of the important thing here is to have a duck string, because that will be the instructions that the AI will have to know how to use your tool. You also have to do that. You also have to do like string output, string input, expression, because this again, it will be turned into instructions to the LLM on how to use the calculator. So in this case, the LLM is told that it can create a string of mathematical calculations, and we will run that through Python. Like we will just run and evaluate the expression, and we'll get the results, and we'll return the strings of those results. We will also give a suite of kind of tax calculation tools to Llama, and these will be those here. Don't need to get into the details, but basically, you know, they also have a duck string. They have an input output duck types, and that's it. Those are different tools like split totals, remove taxes, add taxes, check, calculate taxes, all in the Quebec context, because those are the invoices we have running those. Okay, and we are ready to evaluate if using an agentic system to do that is better. Doesn't start great. Okay, 1 mistake, 2 mistakes. We had 8 out of 11. And so if it does 3 mistakes, it's not better. And this is also more costly because we have to do several AI calls. And now I have 3 mistakes. So I know that it's not worth making an agent here. It's not a program or a task that benefits from that. 8 out of 11, not better. I get the response here, tells me which one are failing, which one are good, and I can move on. Okay, last step. Let's say that I want to see if Gemini is better at being an agent. Well, it's that easy. I'm retaking my program that I have just created here while I was reusing my signature. And now instead of setting LM to Llama, I'm going to set LM to Gemini. My evaluator, I can reuse the same, just passing a different program and run that. So now I can start exploring what AI is better. Of course, in this case, Gemini will be better. It's it's a much bigger model, much better model, but it costs also more. But in this case, I'm kind of want to close the loop and see, can we actually get 11 out of 11 on our invoice? And to do that, I think we need to step up our game and use a bigger model. The other thing we'll do just after that, because now, you know, Gemini is thinking hard, will be to not do an AI agent. Now, see how it's already doing quite a bit better. And we won't do optimization. We're kind of going back to the bases, but we're just being a bit smarter about the outputs that we ask the AI to do. This is just to show how kind of vanilla DSPy, how powerful it is. So we still have our receipt totals output. We have the basic, most simple prompt we had at the beginning. We are still giving our inputs, the receipts, with no questions, no nothing, but we have the instructions. And so that is 10 out of 11. It's not perfect. It had tool, costed quite a bit more. Interesting. Now we're still missing one. Like this one is still wrong. What should we do? And this one is wrong because it's none. It's the none one. And so we could like just add probably to the instruction, you know, it can be none if it's really not there, but it's actually probably the right number. But in my case, it was none. Let's see how we get that to do it. Yeah, so back to it. We're giving the image. This didn't change. We're getting the output. This didn't change. But I am now making it do two things. first thing I'm saying, you will give me a list of floats that will be the items, and I want those to be according to that. So that's a little bit of a string, a prompt that I'm giving. So I want the description and value of each money-related numericals on the receipt. You remember how I was telling you, we get them to kind of output that so that it can use it. That's where we do it. I could be calling chain of thought on top of our intent here, but I'm baking it in here just to show you that it's equivalent. You could be doing that. And so here I'm saying to Gemini, you will output reasoning for us, and the reasoning will be doing that. So thoughts on the actual before and all tax totals, blah, blah, blah. And I'm saying here, none if it's obviously not there. And that's where I'm kind of getting it. I'm kind of, hacking it here so that my none works. And hopefully we get the same result. But last time I ran that, it was 100%. And here it is, 11 out of 11, perfect task, okay? Let's see what I would get with Llama on that task that I get a perfect score. With Gemini, it's still 8 out of 11, and this is the same than our chain of thought from before. It's better than an agent. And and so see how we could easily empirically evaluate, test, move on, iterate, find the best system. If I'm here now and I say, well, you know what, like Gemini is too expensive, but Llama Scout can do it. Let's try Maverick. I can just go get the string for Maverick. I have that here. Can Grok Maverick do it? If there is a context window problem, I will need to get the open router Maverick path. Interesting. Here, see, Maverick is worse than Scout. Fascinating. And I can know that. I can know that with just this change. Amazing. Anyway, so Scout did quite well, but probably that I could try different optimization and Maverick will do it. Maybe I have some things in there that are kind of Llama specific because I've been testing with Llama so much. Works on Gemini. I could do these things here manually. I can use automated optimizer. One cool thing again with DSPy is that if I had a big data set and I controlled my AI because it's let's say an open weight model from Hugging Face, I can just change that here. Instead of this here, I can actually use Bootstrap fine tune. And if I have the right stuff here, can basically do fine tuning on the weights too. And so this is it. In this tutorial, we went from a naive prompt that was getting 2 out of 11 right, and we finished with 11 out of 11 with Gemini and 8 out of 11 with Llama. And we kind of optimized that prompt throughout, because if you don't want to use DSPy to call the program, which I think you should, you may want to pull out now the prompt from this here. And so if you want to pull out the prompt, you will be bringing that system prompt into your other system, and you will want to recreate that template into your other system, and you will be parsing that output here. You could be bringing to your other system, let's say you're using LangChain or whatever, you could be bringing the chat adapter and do the parsing and the formatting with it. That is possible. But again, at this point, I'll just stick with DSPy. If, let's say I have an application where I'm very sensitive to the number of tokens that I am using, and producing those header tokens here for me would not be acceptable. Let's say I just wanted that, then that's where I will do a custom adapter. And so yeah, so this is it. Like DSPy gives you ways to interact with a little bit of everything, Maybe you won't want to use DSPy, you have different tastes, you have different constraints. That's fine. But I believe DSPy, because of all of the pieces that you can play with to affect your prompt, I really believe right now it's the state of the art on how to do prompt engineering, how to do it fast, how to do it easily, organized, evaluate easily, save your program, share your program, do optimization on the weights, do optimizations on the prompts, so on and so forth. Hope you enjoyed this video. Don't forget to like and subscribe.